So, dear ladies and gentlemen, let me start today's webinar on design with a new Dutch Annex in IDEA StatiCa RCS. Better said, in IDEA StatiCa. There is also a beam module which I will show. My name is Navratil. I work as a technical director of IDEA StatiCa company. And as in the last sessions, I prepared some PowerPoint presentation with a list of the topics for today, and with some explanations. I will show you several examples in live presentation. I changed slightly the topic because we will not be speaking about crack width only, and also I would say we will not be speaking about Dutch Annex only, because those things are related to each other. So we know your questions from the questions which you sent us in the past. We would like to introduce new Annex implementation. We want to tell you about the calculation of effective depth in the case of crack width calculation, also how we calculate the crack width in case that we don't find tensile reinforcement in effective embedment zone, how we calculate it in cases that the cross-section is loaded by tensile normal force with small eccentricity. I will mention the checks according to OVS document for railway bridges, and I will mention the differences in evaluation of crack width according to standard Eurocode and Dutch code, Dutch Annex, especially delta sigma P check, and also I will talk about biaxial bending and how we identify reinforcement layers and concrete covers. We start with SR max, which is the maximum distance of the tracks, and as you can see here, there is a different condition for SR max in Dutch Annex. I prepared two examples according to Eurocode and NAN Annex, and you can see the results here. First of all, we have to say that there are different types of combinations: quasi-permanent for standard Eurocode and frequent for Dutch code. It means that sometimes the comparison is a little bit tricky because there are actually different bending moments, different internal forces coming to the calculation. We can see the example. First, I will start with standard EN code. We can see the internal forces. We introduced 37 kilonewton meters as quasi-permanent load. We have the reinforcement of the section. Diameter is 10 millimeters with concrete cover 40 millimeters. When we go to results and crack width, we can see that everything is satisfactory. Crack width is about 70%. The reinforcement is inside of effective embedment zone. We can see SR max 287 and crack width 0.2 millimeters approximately. It should correspond with the first table here. If we open the project for Nano SR max, which is here, again we have same reinforcement, but the internal forces we have to fill in also frequent combination. I calculated this approximately based on the differences between factors. And if we go to results and crack width, then we can see that the crack width is 116%, the utilization, and the crack width is 0.23 millimeters. SR max 260, which is a little bit less than in standard Eurocode. In spite of that fact, the check is more, I would say, demanding or tougher in Dutch Annex. So maybe we can even try if we put here 37, which usually frequent combination would be higher than quasi-permanent, and we go back to the results, and we see short-term effects is 95%. If we check both short-term and long-term, we have 106. So even for the same bending moment as we used for quasi-permanent combination, we get higher utilization according to Dutch Annex, which again confirms that the Dutch code, the Dutch Annex is more demanding than standard Eurocode. If we compare it to the previous Annex, you see that we calculated the same example as I showed you in version 7.15 of IDEA StatiCa and in version 8.0, which was just released. And we see that in old version, the crack width is 0.20, almost 6, and here we have 0.23. So now it is more economic, and also SR max is higher. It corresponds, the old version corresponds with standard Eurocode. Now we have 260 millimeters, which makes it a little bit more economic, so it goes to the less developed cracks or less smaller crack width. I can close these examples. And we can continue in the presentation. The next improvement or method which we introduced into according to new Dutch Annex is the model for nominal stiffness method for second order effect analysis, second order effect calculation. Here you can see the formula used in standard Eurocode, which is given in Eurocode to estimate the stiffness, which should go to the calculation. You can see that there is a contribution of concrete and also contribution of steel. There are, of course, some factors related to cracking and creep, etc. The total bending moment here is calculated as first order moment plus second order moment, and that is calculated as a normal force time the nonlinear deflection. And this nonlinear deflection can be expressed as or the eccentricity, increased eccentricity, as the curvature time the length of the column over C factor, which depends on the curvature distribution. Actually, this part gives us the eccentricity E2. And we can see that the curvature, and we know that the curvature can be calculated as the moment over stiffness, EI. The stiffness, as you can see in the picture here, can be calculated therefore from a moment curvature diagram. You can see that if we have this stiffness, if we put it on the left hand side of the equation, then moment over the curvature gives us the stiffness. Moment over the curvature is the tangent of this angle. That's probably why there is a change in Dutch code, because you can actually calculate the stiffness from moment curvature diagram. And also, if you see this formula M0 plus M2, it is like M0 on the vertical axis plus the increment going in this line as n times the formula which I already introduced. So that is why Dutch code or Dutch Annex replaces modulus of elasticity in the model for nominal stiffness method with effective modulus EF. You can see the table in which you or the program has to interpolate, and we get the new stiffness which is implemented into IDEA StatiCa. We made a comparative calculation for such column, for such non-symmetrically reinforced column, and we see from the results. Here we have a version 7. I don't know what, XX, and version 8. The stiffness in version 7 was significantly smaller than in version 8. That's why also the second order moment is smaller, and you see that the total moment used to be 129, and now we have it 118, 119 possibly. So again, it increases the economy, and we can say that the values taken from the table which I showed before gives us a stiffer column or smaller second order effects. Now I would like to discuss this calculation of the crack width according to EN code and Dutch Annex in more detail, because I believe that Dutch national application makes the crack width check a governing type of the check, governing type of the assessment. For that reason, I want to start a new project. So I start from IDEA StatiCa RCS, and we start a new project according to standard Eurocode, 1D reinforced section and one-way slab. And when the project starts, we can input a new cross-section of one-way slab, will be 200 millimeters deep, and we can go to internal forces. I have to see the internal forces in the document, 60, 50 and 40. So 60 is the bending moment of fundamentally ULS combination, 50 will be for characteristic combination, and 40 is for quasi-permanent, because we still have a standard Eurocode. Then we can go to reinforcement, and if we have this design switched on, we can design the reinforcement based on almost all types of checks, including the crack width. So now it was designed, we can say OK, and we get the reinforcement according to the wish, 80 millimeters distance, and the diameter is 10 millimeters. We can calculate it immediately, and we get the results here. You can see that stress limitation is not satisfactory, but it doesn't matter, or better said, we can explain why the stress limitation failed. IDEA StatiCa doesn't include this check into the design, because actually concrete grade is chosen by the user. We decided about concrete grade here when we selected the dimensions of the cross-section, and in design the reinforcement doesn't help too much with the stress limitation check, because as you can see here in stress limitation we get the critical fiber number 3 in concrete. This is this one. So the check of stress limitations is excluded from the design. All other checks are satisfactory. You see that capacity is almost 98%. If we go to crack width, then we see that it is 0.247. It is satisfactory, and we can also compare it with this. When we go to Dutch National Annex, we will show that we get crack width much higher, for crack width much higher utilization. We see that we go to internal forces and we change this to Dutch National Annex, then a new frequent line or line for frequent combination will appear. We add here 45 and we can calculate it, and we see that it is not satisfactory. We go to results, crack width, this is 0.247, and as it is here for the same reinforcement and actually comparable internal forces, we get much higher utilization of this section. So it means that, in my opinion, Dutch national application makes the crack width check governing type of the assessment. We can even make an experiment, go to internal forces and put here again 40. So same bending moment as for quasi-permanent combination. If we go to results, then we still have 122% of the utilization, which means that these results confirmed the statement here. I have a note here that I should show in this crack width. Sorry, I have to change it back to 45. And I go to crack width, and we can see that long-term effect is 142 and the D is 155. The effective depth of the cross-section is 100 millimeters and 55. If I switch it on here, then you can see the dimension here, 155, which I will compare with the next example. So let's go further. Calculation of effective depth. I want to explain that the effective depth is the distance between the resultant in tensile reinforcement and opposite concrete fiber in compression. In here, we have it, for example, for stress limitation, this is the concrete fiber in compression, so that this is the distance 155. I adapted the ED input and I prepared it before. I can close this one, which was actually input from scratch, and I go to this file in which I can show the internal forces. We have the same internal forces as before, but the reinforcement is different. I only added this reinforcement, top reinforcement close to top fibers. And you can see, if I make it bigger, that we can go even to the results. We can see that crack width is 0.244, but the D is 155, still the same as if we don't have any reinforcement here, yes, same as in a previous example. But for example, in shear analysis, we get D 152. In response, we also have it 152. And there are a little bit different assumptions for the calculation, but the main reason is, and it is written here, that the tensile reinforcement outside, here you see, and it is also in a crack width calculation, you can see the tensile, this reinforcement this is for long-term stiffness frequent combination, and if we go to short-term, then we get it in tension, okay? So this is in tension, and actually it influences the position of the resultant force. but if the tensile reinforcement is outside of the effective embedment zone, then it should not influence the crack width calculation. So that's why we have different results for response and shear and different results for crack width. This top reinforcement, which appeared in tension, was not taken into account for the calculation of the effective depth for crack width calculation. The procedure is like this. First, in first step, we calculate the effective depth in standard way as the distance between the real resultant of tensile reinforcement and opposite concrete fiber in compression. In second step, we calculate the effective embedment zone, HC effective and AC effective. Then in third step, we take the reinforcement from effective embedment zone only, as it is in the code. And we repeat the first step. Of course, if we find this effective depth, then it's okay. We take it as we showed in the example, but it may happen that all reinforcement is excluded because it doesn't go to effective embedment zone. Then this D is calculated or is considered from the first step. So this is the procedure how we do it for the calculation of crack width. Now we can go further to the crack width calculation with no tensile reinforcement in effective area or in effective embedment zone. I will explain this example and then I will show it live. We have a quite heavy reinforcement in the slab. This is the bars are of diameter of 20 millimeters, so half of the diameter is 10 millimeters, and you can see that we have concrete cover 40. If we add 40 plus 10 millimeters as half of the diameter or radius, then we get 50 millimeters. Okay, that is the input, the input of the reinforcement. In that case, if we calculate it, if we calculate the crack width and effective embedment zone, we see that the dimension line shows us the depth of effective embedment zone, this HC effective, only 49.9 millimeters, which means the centroid of the reinforcement is located outside of this effective embedment zone. If this is a text from Eurocode, if there is no bonded reinforcement within the tension zone, we have to use SR max. That's why the results are like this. Crack width is not satisfactory. We can go to the other example or same example with different arrangement. I will open a new data, which is this one, and I will start with this 40 millimeters, as I already explained, the reinforcement. Here we have diameter 20, 50 millimeters, and we go to results, get the utilization, quite big crack width, utilization 115%. Just to see the internal forces which we get, if we switch into the other section with bottom cover 39 millimeters, so we change it only 1 millimeter, the forces are the same, reinforcement is the same, but the concrete cover is 1 millimeter less. And we go to results and we see that everything is okay. We get acceptable crack width 0.179 and the crack width is satisfactory because we found that this reinforcement actually goes to the effective embedment zone, and we can take it into account for the calculation. So this is the result, and we hope we have explained that the program cannot judge if the difference in the distance is 0.1 millimeter or 5 millimeters or 10 millimeters. Simply this is exactly the example on the border. If you change it 1 millimeter, you change completely the method for the calculation, and that's why you get completely different results. I can close this example, and I think I can also close this one. Oh, I will keep it. So we can continue. Next slide is about the calculation of crack width with tensile force with small eccentricity. This has also been improved in IDEA StatiCa. Now we evaluate the crack width separately for each edge of the cross-section, each surface of the cross-section. And if the cross-section is loaded by tensile force with a small eccentricity, we get the distribution of strains as it is in Eurocode. You can see it here. And based on the strains, also the crack width, we display the one, the surface which is critical. In this case, the critical is the bottom one. We can open this tensile force example. Here we have internal forces, quite big tensile force, small bending moments, reinforcement, heavy reinforcement with it is big cross-section. Again, this is a project from our user. And if we go to results, we can see that for crack width, we get this surface of the section as critical, and we calculate the crack width accordingly. If we go to internal forces, and let's say we keep the same bending moment, but we change the sign, minus 110, and we go to results, and the picture is completely different. This top surface is critical, and the crack width should be the same in case that we have the same reinforcement in the top and in the bottom. We can continue with this OVS document or OVS requirements. Actually, this is the special requirement for railway bridges, and we implemented it in IDEA StatiCa. One of the requirements is the requirement that for prestressed structures and for quasi-permanent load, there is a decompression requirement applied for the whole section. It's not about the position of pre-stressing reinforcement, nothing like that. It is strictly required that this decompression reserve is guaranteed in the whole section. So the question was how to evaluate this requirement or this check. As it is compression reserve requirement, we relate it to zero stress here. You see, when we have zero stress, then actually the compression goes to tension, and we know that we have it used for 100%. That's why we developed a special check value in case that we have a stress sigma, compression stress in one fiber of the cross section, and then if they have the same stress in the opposite fiber, we know that it is actually axially compressed and the utilization is 0. In case that there is some decrease of the compression, for example, if we have sigma half or 50% of this stress, then it is 50%. In case that it goes to 0, it is 100. And in case that, for example, there would be theoretically tensile stress equal 50% of this currently acting stress, we would give you the check value 150. It is a little bit tricky because it is related to the stress in compression currently acting, but we believe this will give you quite nice picture about the behavior of the cross-section. The second the second item or thing which I would like to explain is this determination of the zones. Actually, the stress limitations applied according to OVS are dependent on the zone, if the zone is with or without pre-stressing reinforcement. So first of all, we have to find these extreme points, and we do it using the plane of strains, as you can see here in the picture. So it means E1 is the tension point. You see, we call it TP, tension point, because it is located, it is a point, extremely tangent fiber in the cross section. Then we have to determine the zone, if it's with or without pre-stressing reinforcement. You can see here that the tendon T1 is in tension zone. See, it is in tension zone. In case that the dimension x1 T1, this one, is less than this one, x2 T1, related to tendon T1, the extreme point E1 is considered as the point with pre-stressing reinforcement. So we add to this TP plus P, which means that the tendon is located close to this point. Therefore, these OVS conditions are applied for each vertex in relevant zone. If we see this vertex, for example, it is in the zone x1 T1. It means those two vertices are considered as the vertices in the zone with tensile zone with pre-stressing reinforcement. Now then, all vertices localized at this distance. If there is one more vertex, then we would also consider it as TP plus P as a tangent point in the zone with pre-stressing reinforcement. You can see also the explanations in RCS project. We can go to the examples which are here. First, I will open this IDEA beam example. We have such a beam example which we consider as a railway bridge according to Dutch Annex. You can see it here. And if we go to reinforcement, then we see some zones of the reinforcement. Maybe we can also select some other. You see that it is reinforced quite correspondingly to what we expect. And if we go to detail check, then we get we generate the data for the relevant section, and we can calculate it all. And we see that it is not satisfactory. First, even in at the time of pre-stressing, we have 106% of the value, and crack width, it is crack width. We can see results. I switched off all other checks. We go to crack width, and we see the value is 106. That's because the stress here is 0.5. And 0.5 compared to other maybe it is better if we go to the last end of design working life. After this stress increases, then you see that 2.8 megapascals compared to limit value 1.1 is 246%, and you can see it is happening for characteristic combination, and the point was localized as TP plus P, and all these checks according to OVS are recognizable, so you can see how it is done. I can open the other project. For example, here we file save as. We can save it as RCS file, but I have already done it. So we can move to EN code no OVS, which is already RCS project, and if we go to design member, we can see in RCS that this is a road bridge. So I changed the rail bridge into road bridge. This is still Dutch Annex. Okay. Then we go to results, and absolutely the same example. I just saved the data as, and we go to crack width, and everything is okay. Even if we have 0.5, if we go to end of design working life, we have 2.8 megapascals, but simply there is no check of stress limitation, there is only check of crack width. So you can see that the requirements of OVS are much more strict, and that's why for road bridge we have even the utilization is 0, and the railway bridge is much worse. I can switch into this is no OVS. I can switch into the file here, and now above the stress limitation check, we also have maximum allowable reinforcement tensile stress here. You can see it here in the presentation, and it means that the OVS requires minimum amount of reinforcement in tensile zone. We have a tensile zone here, and the non-prestressed reinforcement, there must be some reserve to transmit the tension. That's why we check here also the maximum allowable reinforcement tensile stress. And here you can see that it is 12.1 megapascals compared to 200 megapascals. The value is okay, only 6%, so the check is satisfactory. We can see it here, how we do it. We calculate the resultant tensile force in that tensile area or tension area, and then we check the area of existing reinforcement, of the reinforcement which had been defined in that area. And then we present the check value, which is calculated as the force over the area over 200 megapascals, which is actually the limit which I spoke about. There is one more requirement in OVS, and this is the extension of the table 7.1 of Eurocode, 7.1n of Eurocode. They say in OVS that if you have a lateral reinforcement within a decompression zone, then the crack width shall not exceed 0.1 millimeters. Unfortunately, we cannot check in 1D element what is the lateral reinforcement and all these things. So that's why we have to leave it on the user, and the user can directly modify the limit value in concrete setup, as you can see here in this picture. I can show it also here. If we go to concrete code, we see chapter 7, which is about crack width, and here for Dutch code we have different table, and all these numbers can be changed, and you can simply adapt the limit value, but you have to do it manually, unfortunately. We can possibly close these files, and then we can continue in the presentation the check of delta sigma p. As you can see, the table from Dutch Annex, for elements with bonded pre-stressing steel reinforcement, delta sigma p is checked instead of crack width. It is the last column here, and we should probably explain how we do it. We calculate the state of decompression, which is here, the state in which the stress in concrete is 0. I recall the last presentation, last session, in which I explained it in details. And then we calculate the plane of strain increments starting from the state of decompression, and we calculate the increment, corresponding increment of the stress in pre-stressing reinforcement. When we have it, we compare it with these values in the table. Then there is a coefficient Kx in Dutch code. The coefficient relates the concrete cover really applied to the concrete cover, the nominal concrete cover. In case that it is not the same, then K can be changed, and I just wanted to show you where to edit it. You have to go to design member in RCS, and in design member there is a coefficient Kx. You can change the number 1.0 manually to 1.5 or any number, and then all this crack width effects and also the other delta sigma p are multiplied by Kx factor. Then we have the problem of biaxial load. We can have two examples. Actually, I can open this crack in biaxial bending. This is not the one, sorry. Or I can explain it here. First of all, I defined two layers in a rectangular cross-section. The bottom layer, which is critical for the crack width, has a concrete cover related to bottom surface less than the one which is related to the side. Maybe I can really open this. Yes, here it is. You can see first the uniaxial extreme, and we can go to reinforcement, and if I press to this bottom fiber, you can see that we have edge cover to the H1 30 millimeters, but 40 millimeters to the sides. Of course, the second layer is 70 millimeters, but the same edge cover to the side. When we calculate the crack width, then the concrete cover will be identified as 30 millimeters, not 40. We go to results, crack width, and concrete cover is 30 millimeters here. You can see it here. Okay, it means that the program identified a critical layer and found that the layer is at the distance or with the concrete cover 30 millimeters. In case that we go further to biaxial bending, we still get the concrete cover 30 millimeters. I can show it. I can switch for the same reinforcement, same cross-section. I switch only the extreme to biaxial, and you can see why. Maybe I can rotate it or I can put it back. You can see that even if the gradient of the plane of the strains is inclined, the program identified again the concrete cover 30 millimeters because this bottom layer was identified as a layer, and the concrete cover was found related to that layer. We can see it here in this rules. The rules are like this. We find governing reinforcement bar, one bar. In this case it is this bar at the bottom on the left hand side. Then all bars which are located in one line together with the governing bar are identified. Then we have the lines, and the lines are related to the edges of the cross-section, to the surfaces, and the appropriate bars are recognized as a reinforcement layer, even if you define them as single bars, as the individual bars. And then concrete cover is not identified as the maximum distance of a bar belonging to the layer and the edge, but as the distance of the layer and related edge of the cross-section. So that is what I wanted to show. The last example which we have here, I can close it, is the pile, which is the circular cross-section. We have it here. You can see the reinforcement. This is also an example of one of our old example of one of our customers. We can see internal forces, quite big bending moments. This was Czech customer, so we have it according to Czech code now, but doesn't matter. I just wanted to show in results. I will go to crack width, that in crack width we identify the effective embedment zones in similar way as in biaxial bending. So actually these bars are also identified with the correct concrete cover, but the problem is that we take this effective embedment zone as a whole for the tension stiffening. There's a question what is on safe side, what is not on safe side. We possibly can think about some improvement in this, but I wanted to show this this calculation, this example, to let you know how we calculate it, and possibly we can improve it in future. We know that in case that we have such loading, then this bar number 10 is critical, and we can even possibly under some assumptions calculate the crack width belonging to this single bar. So that was all for today. I just my last picture is a picture which I showed in the first session with which shows the design with IDEA StatiCa, with pre-stressing, construction stages, all these innovative methods, nonlinear creep, visual design. You saw also in this presentation that all the data can be tracked, and we can see it, we can find it in the program, and also innovative methods such as interaction of internal forces and all of these. I thank you for your attention, and possibly we have some questions. Do we have, Alex, some questions? I didn't check it.
Yes, we've got a question. Lim differs. Is that because of SR max or other difference? That's the first question.
I do not know now in which example it was. SR max, yeah, it was probably the first one. We'll see. It was this one. Where Lim differs. I will see if it is correct. I will open. We'll close this one. and I can open Encode NEN SR Max. We have several other questions I can see now. No, we have many questions. Maybe Dennis van Kaan can write me in the chat if it was this NEN SR Max RCS. Volume differs. Results. Crack width. Yes, of course. This was Dutch code, and the other one was Encode, standard Encode. So there are different. There is different. This table. I can show it. I can show it here. The table 7. This table differs from the table of standard Eurocode. If I switch the code back to Encode, to standard EN, okay. Then for the same, if we go to design member, then for the same exposure classes, we get different table. Okay, so the limit value of the crack differs. That's true. Then we have long questions. Yes, it was the very differs. Okay. I can read it now. In the example of HC effective without reinforcement in the effective zone, IDEA found large difference between the check with 0.0 and the concrete cover. Oh, those are quite too conservative. Can you explain why there is chosen this assumption? I'm reading this question because we have to. I have to understand it. Wilfried Wischer, or Wischer, I do not exactly know the pronunciation, asks about the way of calculation of epsilon SM minus epsilon CM, and that we use the coefficient 1.0 times sigma S over ES instead of 0.6. I must say that I do not know exactly now why we do it. The question is that it seems to be too conservative. Can you explain why there is chosen this assumption? Maybe Peter can help me, because I do not remember now why we use 1.0 instead of 0.6. Peter, are you here? Or we can also answer the question by email. Peter? I try to check the other question. For long-term crack width calculation, we use the effective modulus of elasticity. So it is E over 1 plus 5 function. Yes.
Do you hear me? I have switched the
yes,
microphone.
yes.
It will be better to write down to email the answer.
So you are not sure now?
I'm not sure now, yeah.
Okay, thank you. But in the code check formula for alpha E, the short term is used. And yes, we use, actually, I do not know if I follow the question exactly, but I can show if I go back to Dutch code, then I go like this, and I go to results, crack width. We calculate both short term, which is EC, and long term EC m over 1 plus phi function, and we present also the value 116%, 130%. So we calculate both and we evaluate both, and then we take into this evaluation the bigger one. So we do use both moduli of elasticity, if that was the question. Then there is a question, just a second. Oh, I cannot see the questions. I'm trying to get the questions so that I can read them. Okay. If the section remains uncracked in frequent combination, there is no check according to 732 from Eurocode applied. There was a question, not this question mark. In the section. And for regular projects, according to OVS, the minimum reinforcement should be tensile force area over the, is that in, we do not design the minimum reinforcement for OVS. We only check if the amount of reinforcement which is defined by user is satisfactory, is enough. So that is the second part of the question, and first part of the question. I do not know if I understand exactly, but you can see it here. We have it on ribbon now. We can select either no resistance of concrete in tension, or no resistance, it is in extreme now, or in section only always. If I say always, now I have one extreme, but if you have in section, if you have like many extremes, then for all extremes in that section, we exclude the tension. In the case that we have always, then we always exclude the tension, and it is described in the tooltip. The assumption that the concrete resists no tension will be applied in all SLS checks for all combinations of all sections and their extremes. So you can influence it by, or you can change it by these settings, and I see if that was the question, because the question was if the section remains anchored in frequent combination, there is no check according applied. If there is other combination in which we get the cracks, then based on the settings here which I showed, we calculate the cracks. So that's it. If there is no crack, from none of the combinations which are in the project, then we do not check the crack width unless it is OVS, and then we have to check this stress limitation, this compression reserves, and all these things. Then we have a question. I do not know if I, please, if I did not understand your question properly, or if I didn't answer correctly, then let me know by email. I would be very happy to discuss it by email. Which the user or the guy who asked says yes, by email is okay. So there are no other questions. Then I would like to thank you for your attention, and Thank you. Yeah, okay, thank you. And as I said, we can discuss those things via emails, or I plan to visit Netherlands and to make a roadshow together with our distributor Emil Peltenburg, and we can possibly meet. Possibly we have already agreed the meetings, so we can discuss it personally, which I am looking forward. Thank you very much, and bye-bye for now.